Well, thank you very much for being here for this protocol spotlight interview with Dr. Ray Truant. Dr. Truant completed his bachelor's degree at the University of Toronto and continued on to his graduate studies at the C.H. Best Institute. Ray did his postdoctoral training at the Howard Hughes Medical Research Institute at Duke University. In 1999, Ray was appointed assistant professor in the Department of Biochemistry at McMaster University, where he started new projects on polyglutamine diseases, focusing on Huntington's disease. Today, we will be discussing his lab protocol paper and associated protocol in protocols.io, MOD3D, a low-cost, flexible modular system of live cell microscopy chambers and holders. Ray, thank you so much for sparing some time to talk to us.
Thanks.
Could you please briefly explain what this protocol is about, how to use it, and why it is relevant?
So the protocol is basically taking advantage of really low-cost consumer electronics 3D printing, which is slowly seeping its way into most labs in biomedical research, simply because of the number of different things you can do with it at relatively low cost. What we're specifically addressing is my lab does a lot of live cell microscopy based assays and cell biology, and we go through a tremendous amount of fabricated live cell imaging chambers that we get from suppliers that are expensive. We can roughly spend anywhere between $12,000 and $14,000 a year on these chambers, and from talking to my students and people in the lab, they were also concerned about the way that we were using plastic consumables in the lab and how much waste there was. And we certainly generate a ton of waste in most biomedical research labs, mostly in the form of polystyrene, which is a plastic that does not really get recycled easily and does not break down in the environment. So we looked at whether there was some methodology that we could use to fabricate our own 3D imaging chambers and plates within the lab, but also keep in mind in the design on how to minimize the use of plastic, and in particular, the waste of plastic. So we ended up with the modular concept because what it allows people to do is only use the number of wells that they need per the experiment and customize the type of well they need for that experiment and not have any unused wells on a plate, because typically these plates are used once and then tossed in the trash. And for the plastic that we're using, we wanted to focus in on a biodegradable plastic, which ended up being polylactic acid, or PLA. We struck a significant number of challenges. I'm not an engineer, but all of a sudden I had to learn all the tricks and the trades of engineering, including computer-aided design. The 3D printing part was actually not difficult. It was the technical aspects of it and development of it, the practical development of it, that turned out to be technically important, because at the end of the day, a protocol is useless if it's too complex or too finicky for the member of the lab to use. And we chose this format because we're using it as a lab resource. My lab functions under open science, so we share everything. We have an extremely collaborative community in Huntington's disease research, so it's part of that as well. So the whole system, the prints, everything are freely available for people to download and use. Even though there is a patent applied to it, it doesn't apply to people who want to just go ahead and manufacture themselves.
So you published this paper a little bit over a year ago. Can you describe how it integrates in what was the state of the art at the moment? Meaning, you have described very well what the motivations were, but was there anybody else doing 3D printing to create their own affordable or reusable or environmental friendly changes?
So 3D printing has the papers had started to appear around that period of time, but there were only about 3 manuscripts in total that I've seen related to cell biology and microscopy use. And those papers typically use the 3D print format as a way to make a mold to cast a type of chamber in some type of safe silicone that doesn't have any toxicity to the samples. And this was a big problem in the early days. So when we tried to initially apply this technology, we found that most of the resins and plastics that were available to the consumer industry were simply far too toxic for mammalian tissue culture cell growth. So we actually shelved the project for a while. We concluded it wasn't going to work. And then a few things changed. All of a sudden, new plastics started appearing at very low cost. And those plastics were PLA based, and they were advertised as non-toxic. So we tried them, and we in fact found that out to be true, which regenerated interest in the project. And then as we're developing this, the technology on 3D printers available through the consumer market, which is really what most labs are buying from these days at a low cost, they're getting significantly cheaper every year. And the quality of what they're able to do is increasing every year. A lot of that has to do simply with patent expiration. And so what was, a lot of us looked at 3D printers in the early 2000s, and it meant spending upwards $50,000 to $75,000 per lab, very hard to justify. These days, they're down to $500 or less. And some of the printers can offer you micron resolution, which is actually incredible when you think about it.
Thank you so much. And I see that, from your description, you tackled several angles by creating this protocol. But in addition to the time you're investing in developing this protocol, what was the motivation? I understand that you make everything available, but what was the motivation to go one step further and have the protocol peer-reviewed and published as an indexed paper and not just in the platform?
Right. So, if we could have developed the protocol within the lab and just kept it within the lab, but I didn't really see a benefit to that. I mean, for our motivation was to save money. And then after we had successfully developed these chambers, we realized that, there is a lot of teaching labs at the level of high schools or even at smaller universities that simply don't have the budget to afford to buy these commercial chambers. If they went and printed out their own, because most of these labs now have 3D printers, it's almost no cost. And that was an impact that we saw. We wanted to use this protocol's format, as a lab resource. I have a lab of about 14 people. There's turnover every 2 or 3 years with graduates. It's nice to have them to go back and look at one common updated protocol that retrains people without having to take time from other people in the lab. And when you're training people on a protocol, for everyone to work on the same page from the same protocol is really important. Because if you have sort of a protocol floating around the lab unofficially, it can morph depending on different users and end up being very frustrating at the person at the end of that after 2 or 3 years. This keeps us all on one page. And as we learn more, we benefit the protocol by updating it, and that benefits the users at the end of it. And we also realize that for something that is so common that could be used in any cell biology lab, the potential for citations on this paper and on this protocol could be potentially very high.
And could you then elaborate on the feedback that you received from peer reviewers? How did it shape the final version of the protocol?
Well, they looked at it with different eyes. We came at it as a sort of from a practical nature. What they came at it in the reviews was a little more skeptical. They wanted to know, okay, is this really practical? For example, they asked us, could you do an assay to show us and to quantify with very high numbers the potential for any toxicity of this plastic, because it was clear that peer reviewers have had experience with this. And prior to this paper, I'm pretty sure they had the experience of toxicity whenever they tried to apply any of these plastics to tissue culture growth. So they wanted us to prove that, in fact, was the plastic non-toxic, was the final version of the chambers non-toxic. They also helped me out with some reviews that I didn't, other references that I missed, because it's kind of hard to find references if they're not specifically highlighted on, our biomedical resources like PubMed. So they did highlight a few other, technical papers that were out there where people were looking into things, some interesting reviews on material science and chemistry behind this technology that I was unaware of, that ended up being very helpful for us to understand the nature of the toxicity of these plastics.
And what was the reason that you decided to make the peer review history public together with the paper?
Well, I try and do this with any manuscript that we publish. Again, just on the philosophy of the lab, which is open science. And I think it's important for people to see the reviews on a manuscript, just to ensure that the manuscript was in fact diligently reviewed. And you can see from these reviews, they did pay very close attention to every single figure and asked a lot of good questions. And the first version of the manuscript went up on an archive, and you can see that the final version that was published was a better manuscript, simply because it got input from the reviewers and was improved.
And I would like us now to delve a little bit more on the manuscript itself and the protocol itself. And, behind the scenes, I would like to know if there's anything that you tried while developing these chambers that didn't work and didn't make it to the final version of the protocol.
Yeah, so we had a lot of failures. I mean, we tried different ideas, and we were interested in, in early days, we found out that the adhesives that we were using to glue the cover slips to the plastic were inherently toxic. So we figured out we needed a way to get around adhesives. And we tried to use self-assembling magnetic structures and using gaskets to see if that would work. And we found out that plastics there's a reason why the industry mostly uses polystyrene. The reason why they mostly use polystyrene is polystyrene does not absorb moisture, and it really doesn't thermally change when you go from 37 degrees back to room temperature, or you go from ice up to 37 degrees. And we were finding the plastics absorb moisture. So when you put them inside of an incubator, which is rich in moisture, they would change their parameters, they would loosen up, they would start to leak. So we had to get away from the idea of a gasket approach and go back to an adhesives approach. And then we found out that the industry that makes these types of chambers commercially, where they adhere cover slip glass or sheets of cover slip glass to plastic, they guard these adhesives as an industry secret, which meant we weren't going to get any help. And we had to go out on our own and work with companies that did specifically do nothing but make adhesives. And again, they're a little bit guarded because they can't tell you secrets from their largest customers. So we ended up finding a silicone adhesive supplier who had a wide range of adhesives that had been certified, FDA certified for biological implants in people. So we started from there, arguing that that was probably the least toxic solution. And there was just a lot of trial and error. So we end up with an entire set of drawers full of glues that just didn't work, were not practical. We had designs that we thought were practical, but then, we found out a problem in the incubation where they would warp, or they would stretch, they would leak. We found out that we had to optimize for the design of the chambers when they actually got onto the microscope, to make sure that the focal plane of the glass was equivalent to a typical standardized plate, so that it could work with any microscope. So we ended up, working on a standardized 96-foot well format, which has it has a standard format in the industry. Everyone uses it, and all microscopy companies design their devices to use those style of plates. So we were constrained within those parameters, and then we had to figure out, how to get things working with solely that application. So yeah, there was a lot of error before the success.
So what would you say then are the most critical steps in the building of these chambers?
We thought the most critical steps would be maintaining sterilization, and that turned out to be relatively trivial. Just using alcohol solutions and ultraviolet light. So we actually don't have that as an issue. What we found as a major issue was, once we found a non-toxic resin from a supplier, you had to stick to that and not deviate, because you don't know what formulations are coming from other companies. And if people can't source the exact resin that we can in North America, they're all sourced originally from Chinese factories, but if they can't get that original resin, they are going to have to troubleshoot and try the resins that they can source locally. And a similar problem with the glue. If you can't get room temperature vulcanized silicone with those low toxicity formulas that were listed in the suppliers in the protocol, if you can't get that in your region, you're going to have to try what you can get in your region. Generally speaking, from what I've heard of people, if they can get adhesives that are used in the aquarium industry, they're generally non-toxic. And people are really careful about that, because people will spend thousands of dollars on exotic fish in their aquarium, and they don't want them to die because of the glue that they use to adhere their aquarium together.
Absolutely. So, in addition to the glue and the resins, have you had any troubleshooting since the time of publication?
We've changed some designs a little bit. We get a sort of a practical nature when you start getting multiple people. Originally, it was just the original authors that were making the chambers. And we were sort of getting feedback from, this was typically something that was put into the hands of a young student coming into the lab at the undergraduate level, that's like, okay, well, you're going to do a production of these for a couple of weeks, and this is going to supply the lab for 6 months, kind of thing. And we were then getting feedback from them where they were saying certain aspects were a little bit more difficult. It would be, nicer if the wells had a bit thicker plastic for rigidity and to hold more glue for adherence. And they modified the protocol a little bit. We found out that for any of these RTV silicones, the step of incubating in water is really important. It helps accelerate the curing of the silicones. And by doing that, it removes any toxicity from uncured silicone. And I think it also has a role in washing out any toxins from the UV cross-linked plastics.
And so what would you say has been the significance of publishing the protocol and the paper for your career and those of the younger folks in your lab?
So it's the first time we've done this through Protocols.io, right? And we originally had goals, in this particular project. We now see, for other protocols that we develop in the lab, we are very interested in technology development for live cell imaging and fluorescence microscopy. We have other protocols that we are planning to publish. So just going through that procedure turned out to be useful to us, but we're also seeing the value of having a centralized protocol, not just for our lab, even not, outside of the community. But again, it goes into the whole philosophy of the whole point of what we're doing here at a university is to share information. And this is just a really good way to share information. And if it doesn't work and it's not practical, people are not going to use it. So, I really like the aspect of being able to update and modify the protocols as things change, because they always do. Suppliers change. Since 2020, getting supplies into a lab in general has been a challenge worldwide. Supply lines just dry up. Suddenly, about 6 months ago, a major supplier of glass bottom 96 well plates stopped making them. So these are and we, in fact, when we were developing the protocol, one unintended benefit that we found out was when supply lines cut down in late 2020 and into 2021, we simply could not get chambers purchased commercially. So we were making them all internally. Then we see the advantages of there's no wait times. If we don't order and have something show up 2 weeks later, we can make it and get it working within a day and a half or so. We can stock it up in the lab and never run out. Those aspects have been very beneficial to us. So it's more about transitioning my lab over into a completely digital realm where we're now in digital notebooks. We are in open science and all aspects of open science. We contribute to that with our protocols as well. And this is just another piece of that puzzle.
So Ray, it's been a really engaged and illuminating conversation. And just before we wrap up, I would like to know if there's anything else that you would like to mention that we haven't discussed so far.
No, I don't think so. I think it's worth a try, but I mean, if people really want to take this on, be aware that it is going to require an investment of time, and it is the perfect project for an undergraduate in a cell biology lab to get their feet wet, to come in, learn some technology and learn some microscopy before they get on, and it will benefit the entire lab as they bring it in. In terms of the investment into these 3D printers, I would not balk at their cost, even at the highest end. So it has been very clear to us that whatever they cost, they pay for themselves in a matter of weeks. And they will benefit your lab's budget and time in a significant manner. And time, of course, is money in any situation.
Well, Ray, thank you so much. I will bid farewell. And again, thank you.
Thanks.